Good day. For this video, I'm going to discuss about the water treatment. This topic includes water quality, coagulation, softening, mixing and flocculation, sedimentation, filtration, disinfection, adsorption, membranes, water plant residuals, and management. Water quality. Precipitation in the form of rain, hail, or sleet contains very few impurities. It may contain trace amounts of mineral matter, gases, and other substances as it forms and falls through the Earth's atmosphere. The precipitation, however, has virtually no bacterial content. Once precipitation reaches the Earth's surface, many opportunities are presented for the introduction of mineral and organic substances, microorganisms, and other forms of pollution. When water runs over or through the ground surface, it may pick up particles of soil. This is noticeable in the water as cloudiness or turbidity. It also picks up particles of organic matter and bacteria. As surface water seeps downward into the soil and through the underlying material to the water table, most of the suspended particles are filtered out. This natural filtration may be partially effective in removing bacteria and other particulate materials. So there are four categories are used to describe drinking water quality. First is the physical, second is the chemical, third is the microbiological, and lastly is the radiological. Physical characteristics includes turbidity of the water, color, taste and odor, and temperature. Turbidity is the presence of suspended materials such as clay, silt, finely divided organic material, plankton, and other particulate material in water. Color is dissolved organic material from decaying vegetation, and certain inorganic matter cause color in water. Occasionally, excessive blooms of algae or the growth of aquatic microorganisms may also impart color. Taste and odor in water can be caused by foreign matters such as organic compounds, inorganic salts, or dissolved gases. These materials may come from domestic, agricultural, or natural sources. Temperature. The most desirable drinking waters are consistently cool and do not have temperature fluctuations or more than a few degrees. Groundwater and surface water from mountainous areas generally meet these criteria. In chemical characteristics, there are classifications of chloride, fluoride, iron, lead, manganese, sodium, sulfate, zinc, arsenic, toxic inorganic substance, and toxic organic substance. Chloride. Most waters contain some chloride. The amount present can be caused by leaching of marine sedimentary deposits or by pollution from sea water, brine, or industrial or domestic wastes. Fluoride. In some areas, water sources contain natural fluoride. Where the concentration approach optimum levels, beneficial health effects have been observed. Iron. Small amounts of iron frequently are present in water because of the large amount of iron in the geological materials. The presence of iron in water is considered objectionable because it imparts a brownish color to laundered goods and affects the taste of beverages such as tea and coffee. Lead. Exposure of body to lead, however brief, can be seriously damaging to health. Prolonged exposure to relatively small quantities may result in serious illness or death. Lead taken into the body in quantities in excess of certain relatively low normal limits is a cumulative poison. Manganese imparts a brownish color to water and to cloth that is washed in it. It flavors coffee and tea with a medical taste. Sodium. The presence of sodium in water can affect persons suffering from heart, kidney, or circulation ailments. Sulfate. Waters containing high concentrations of sulfate caused by leaching of natural deposits of magnesium sulfate or sodium sulfate may be undesirable because of their laxative effects. Zinc. is found in some natural waters, particularly in areas where zinc ore deposits have been mined. Zinc is not considered detrimental to health, but it will impart an indesirable taste to drinking water. Arsenic occurs naturally in the environment and is also widely used in timber treatment, agricultural chemicals, and manufacturing of gallium arsenide wafers, glass, and alloys. Arsenic in drinking water is associated with lung and urinary bladder cancer. Toxic inorganic substances. Nitrates, cyanides, and heavy metals constitute the major classes of inorganic substances of health concern. Methemoglobinemia, or infant cyanosis or blue baby syndrome, has occurred in infants who have been given water or fed formula prepared with water having high concentrations of nitrate. Toxic organic substances. These are over 120 organic compounds listed in the U.S. Environmental Protection Agency's Priority Pollutant List. These include pesticides, insecticides, and solvents. Like the inorganic substances, their effects may be acute or chronic. Microbiological characteristics. Water for drinking and cooking purposes must be made free from disease-producing organisms or pathogens. These organisms include viruses, bacteria, protozoa, and helminths. Some organisms which causes disease in people originate with the fecal discharges of infected individuals. Others are from the fecal discharge of animals. Radiological characteristics. Development of used atomic energy as a power source and the mining of radioactive materials as well as natural occurring radioactive materials have made it necessary to establish limiting concentrations for the intake into the body of radioactive substances, including drinking water. The effects of human exposure to radiation or radioactive materials are harmful, and any unnecessary exposure should be avoided. Humans have always been exposed to natural radiation from water, food, and air. Let's proceed to water classification and treatment system. Water classification by source or potable water is most conveniently classified as to its source, that is groundwater or surface water. Generally, groundwater is uncontaminated but may contain aesthetically or economically undesirable impurities. However, groundwaters can be influenced by man-made spills and become contaminated. Surface water must be considered to be contaminated with bacteria, viruses, or inorganic substances that could present a hard health hazard. Treatment systems. Treatment plants can be classified as simple disinfection, filter plants, or softening plants. Plants employing simple chlorination are usually groundwater sources that have a high water quality and chlorinate to ensure that the water reaching customers contains safe bacterial levels. A groundwater source can contain naturally occurring contaminants such as arsenic, fluoride, radionuclides, iron, or manganese. In this case, the water may be treated by absorption, ion exchange, or precipitation processes to remove the contaminant. Groundwaters can be also contaminated by spills caused by humans. Infiltration plant, rapid mixing, flocculation, sedimentation, filtration, and disinfection are employed to remove color, turbidity, taste, and others, organic matter, and bacteria. So this is the flow diagram of a conventional surface water treatment plant or filtration plant. And this one is the flow diagram of water softening plant. Now let's proceed to water treatment. First is the coagulation. Surface waters must be treated to remove turbidity, color, and bacteria. When sand filtration was developed around 1885, it became immediately apparent that filtration alone would not produce a clear water. Experience has demonstrated that filtration alone is largely ineffective in removing bacteria, viruses, soils, particles, and color except at very low loading rates, which is impractical for all but very small utilities. The objective of coagulation and subsequently flocculation is to turn the small particles of color turbidity, and bacteria into large flocks either as precipitates or suspended particles. These flocks are then conditioned so that they will be readily removed in subsequent processes. Technically, coagulation applies to the removal of colloidal particles. Coagulation in this chapter will refer to colloid removal only. We define coagulation as a method to alter the colloids so that they will be able to approach and adhere to each other to form largely flocked particles. Colloid stability. The colloids are suspended in solution and can't be removed by sedimentation or filtration. Very simply, the particles in the colloid range are too small to settle in a reasonable time period and too small to be trapped in the pores of a filter. For colloids to remain stable, they must remain small. Most colloids are stable because they possesses a negative charge that repels other colloidal particles before they collide with one another. Colloid stabilization. Colloids are stable because of their surface charge. In order to destabilize the particles, we must neutralize this charge. Some neutralization can take place by the addition of ion of opposite charge to the colloid. Since most colloids found in water are negatively charged, the addition of sodium ion Na1 should reduce the charge. Coagulation. The purpose of coagulation is to alter the colloids so that they can adhere to each other. During coagulation, a positive ion is added to water to reduce the surface charge to the point where the colloids are not repelled from each other. A coagulant is a substance chemical that is added to the water to accomplish coagulation. There are three key properties of coagulant. First is trivalent cation. As indicated in the last section, the colloids most commonly found in natural waters are negatively charged, hence a cation is required to neutralize the charge. A trivalent cation is the most efficient cation. Non-toxic. This requirement is obvious for the production of safe water. The third, insoluble in the neutral pH range. The coagulant that is added must precipitate out of solution so that high concentrations of the ion are not left in the water. Such precipitation greatly assists the colloid removal process. So, the four basic types of coagulant aids. First is the pH adjuster, second is the activated silica, third is clay, and fourth is polymers. Let's proceed to softening. First, a classification is hardness. The term hardness is used to characterize a water that does not lather well, causes a scum in the bathtub, and leaves hard, white, crusty deposits scale on coffee pots, tea kettles, and hot water heaters. The failure of lather will in the formation of scum on bathtubs is the result of the reactions of calcium and magnesium with the soap. So, hard water classification has ranges. Hard ranges from milligram to liter. In the description is here 0 to 75 is soft, 75 to 100 is moderately hard, 100 to 300 is hard, and greater than 300 is very hard. Lime soil softening mode. More advanced concept in lime soil softening, estimating carbon dioxide concentration, softening to particle limits, ion exchange softening. Mixing and flocculation. Mixing or rapid mixing as it is called, is the process whereby the chemicals are quickly and uniformly dispersed in the water. Ideally, the chemicals would be instantaneously dispersed throughout the water. During coagulation and softening, the chemical reactions that take place in rapid mixing from precipitates either aluminum hydroxide or iron hydroxide from during coagulation, while calcium carbonate and magnesium hydroxide form during softening. During coagulation and softening, the chemical reactions that take place in rapid mixing form precipitates. Either aluminum hydroxide or iron hydroxide form during coagulation, while calcium carbonate and magnesium hydroxide form during softening. The precipitates formed in these processes must be brought into contact with one another so that they can agglomerate and form larger particles, called flux. This contacting process is called flocculation and is accomplished by slow, gentle mixing. In the treatment of water and wastewater, the degree of mixing is measured by the velocity gradient g. The velocity gradient is best thought of as the amount of shear taking place. That is, the higher the g value, the more violent the mixing. Rapid mix. Rapid mixing is probably the most important physical operation of affecting coagulant, thus efficiency. Rapid mixing can be accomplished within a tank utilizing a vertical shaft mixer. Flocculation. The objective of flocculation is to bring the particles into contact so that they will collide, stick together, and grow to a size that will readily settle. Enough mixing must be provided to bring the flock into contact and to keep the flocks from settling in the flocculation basin. Sedimentation. Particles that will settle within a reasonable period of time can be removed in a sedimentation basin, also called a clarifier. Sedimentation basins are usually rectangular or circular with either a radial or upward water flow pattern. Regardless of the type of basin, the design can be divided into four zones: inlet, settling, outlet, and sludge storage. So, zones of sedimentation tank. Sedimentation concept. There are two important terms to understand in sedimentation zone design. The first is the particle settling velocity. The second is the velocity at which the tank is designed to operate, called the overflow rate. The determination of velocity. In design of an ideal sedimentation tank, one first determines the settling velocity of the particle to be removed and then sets the overflow at some values less than or equal to settling velocity. Determination of the particle settling velocity is different for different types of particles. Settling properties of particles are often categorized into one or three classes. Type 1 sedimentation is characterized by particles that settle discretely at a constant settling velocity. They settle as individual particles and do not fluctuate or stick to other particles during settling. Examples of these particles are sand and grit material. Generally speaking, the only application of type 1 settling is during pre-sedimentation for sand removal prior to coagulation in a potable water plant and settling of sand particles during cleaning of rapid sand filters and in the grit chambers. Type 2 sedimentation is characterized by particles that flocculate during sedimentation. Because they flocculate, their size is constantly changing. Therefore, the settling velocity is changing. Generally, the settling velocity is increasing. This type of particles occur in alum or iron coagulation, in primary sedimentation, and in settling tanks in trickling filtration. Type 3 or zone sedimentation. In zone sedimentation, the particles are at high concentration greater than 100 mg per liter, such that the particle tend to settle as a mass. Is a distinct clear zone and sludge zone are present. Zone settling occurs in the lime softening and sedimentation, activated sludge sedimentation, and sludge thickness. Determination of velocity. There are different ways to determine effective particles settling velocity and consequently to determine overflow rates. First is discrete settling. In the case of type 1 sedimentation, the particle's settling velocity can be calculated and basin designed to remove a specific size particle. Next treatment is filtration. Water filtration is a process for separating suspended or colloidal impurities from water by passage through a porous medium, usually a bed of sand or other medium. Water fills in the pores, open spaces between the sand particles, and the impurities are left behind, either clogged in the open spaces or attached to the sand itself. Methods of classifying filters. According to the type of medium used, such as sand, coil called anthracite, dual media, or mixed media. By allowable loading rate is the flow rate of water applied per unit area of the filter. It is the velocity of the water approaching the face of the filter. Disinfection is used in water treatment to reduce pathogens to an acceptable level. Disinfection is not the same as sterilization. Sterilization implies the destruction of all living organisms. Drinking water needs to be sterile. Three categories of human enteric pathogens are normally of consequence: bacteria, virus, and amoebic cysts. Purposeful disinfection must be capable of destroying all three. To be of practical service, such water disinfectants must possess the following properties. They must destroy the kinds of numbers of pathogens that may be introduced into water within a practicable period of time over an expected range in water temperature. They must meet possible calculations in comparison concentration and condition of waters or wastewater to be treated. They must be neither toxic to humans and domestic animals nor unpalatable or otherwise objectionable in required concentrations. They must be dispensable or reasonable cost and safety and easy to store, transport, handle, and apply. Their strength or concentration in the treated water must be determined easily, quickly, and preferably automatically. They must persist within disinfected water in a sufficient concentration to provide reasonable residual protection against its possible recontamination before use or because this is not a normal attainable property. This appearance of residuals must be a warning that recontamination may have taken place. Disinfection kinetics. Under ideal conditions, when an exposed microorganism contains a single site vulnerable to a single unit of disinfectant, the rate of die-off follows Chick's law, which states that the number of organisms destroyed in a unit time is proportionally to the number of organisms remaining. Chlorine reaction in water. Chlorine is the most common disinfecting chemical used. The term chlorination is often used synonymously with disinfection. Chlorine may be used as the element C2 as sodium hypochlorite and or calcium hypochlorite. When chlorine is added to water, a mixture of hypochlorous acid and hydrochloric acid is formed. Chlorine disinfecting action. Chlorine disinfection involves a very complex series of events and is influenced by the kind of extent of reactions with chlorine reactive materials, including nitrogen, temperature, pH level, and availability of test organisms and numerous other factors. Such factors greatly complicate attempts to determine the precise mode of action of chlorine on bacteria and other microorganisms. Chlorine or ammonia reactions. The reaction of chlorine with ammonia are of great significance in water that contains natural or added ammonia. The ammonia reacts with hydrochloride to form various chloramines which, like hydrochloride, retain the oxidizing power of the chlorine. Practices of water chlorination. The evolution. Early water chlorination practices, variously termed plain chlorination, simple chlorination, and marginal chlorination, were applied for the purpose of disinfection. Chlorine ammonia treatment was soon thereafter introduced to limit the development of objectable tastes and odor, often associated with marginal chlorine disinfection. Combined residual chlorination. Combined residual chlorination practice involves the application of chlorine to water in order to reproduce with natural or added ammonia, a combined available chlorine residual, and to maintain that the residuals are part of all of a water treatment plant or distribution system. Free residual chlorination. Free residual chlorination practice involves the application of chlorine to water to produce either directly or through the destruction of ammonia, a free available chlorine residual, and to maintain that residual through part of all of a water treatment plant or distribution system. Free available chlorine from forms have higher oxidation potentials than combined available chlorine forms and therefore are more effective as oxidants. Chlorine dioxide. Another very strong oxidant is chlorine dioxide and is formed on-site by combining chlorine and sodium chloride. Chlorine dioxide is often used as a primary disinfectant, inactivating the bacteria and cysts, followed by the use of chloramine as a distribution system disinfectant. Chlorine dioxide does not maintain a residual long enough to be useful as a distribution system disinfectant. The advantage of chlorine dioxide over chlorine is that chlorine dioxide does not react with precursors to form the BPS. Ozonation. Ozone is a pungent smelling, unstable gas. It is a form of oxygen in which three atoms of oxygen are combined to form the molecule O3. Because of its instability, it is generated at the point of use. The ozone generating apparatus commonly is a discharge electrode. To reduce corrosion of a generating apparatus, air is passed through a drying process and then into the ozone generator. Advanced oxidation process. Advanced oxidation process are combinations of disinfectants designed to produce hydroxyl radicals. Hydroxyl radicals are highly reactive, non-selective oxidants able to decompose many organic compounds. Most noteworthy of the advanced oxidation processes is ozone plus hydrogen peroxide. Adsorption. Adsorption is a mass transfer process wherein a substance is transferred from the liquid phase to the surface of a solid where it is bound by chemical or physical forces. Generally, in water treatment, the adsorption solid is activated carbon, either granular or powdered PAC. Powdered PAC is fed to the raw water in a slurry is generally used to remove taste and odor causing substances or to provide some removal of synthetic organic chemicals. GAC is added to the existing filter system by replacing the anthracite with GAC or other an additional contactor is built and is placed to the flow scheme after primary filtration. The design of GAC contactor is very similar to the filter box, although deeper. Membranes. A membrane is a thin layer of material that is capable of separating materials as a function of their physical and chemical properties when a driving force is applied across the membrane. In the case of the water treatment, the driving force is applied by using a high-pressure pump and the membrane type is selected based on the constituents to be removed. Water plant residuals management. When precipitated chemicals and other materials removed from raw water to make it potable and palatable are termed residuals. Satisfactory treatment and disposal of water treatment plant residuals can be the single most complex and costly operation in the plant. Residuals withdrawn from coagulation and softening plants are composed largely of water, and the residuals are often referred to as sludge. Water plant and residual management. As much as 98% of the sludge mass may be water. Thus, for example, 20 kg of solid chemical precipitate is accompanied by 980 kg of water. Assuming equal densities for the precipitate and water, approximately 1 cubic meter of sludge is produced for each 20 kg of chemicals added to the water. For even a small plant, this might mean up to 800 cubic meter per Y of sludge, a substantial volume to say the least. Water treatment plant and residuals they produce can be broadly divided into four general categories. First are those treatment plants that coagulate, filter, and oxidize a surface water for removal of turbidity, color, bacteria, algae, some organic compounds, and often iron and or manganese. These plants generally use alum or iron salts for coagulation and produce through waste streams. The second type of treatment plants are those that practice softening and removal of calcium and magnesium by the addition of lime, sodium hydroxide, and or soda ash. These plants produce clarifier basin sludge and SFBW. The third type of plants are those that are designed to specifically remove trace organics such as nitrate, fluoride, radium, arsenic, and so forth. These plants use for processes such as ion exchange, reverse osmosis, or adsorption. These produce liquid residuals or solid residuals such as spent adsorption material. The fourth category of treatment plants are those that produce air phase residuals during the stripping of volatile compounds. The major types of treatment plant residuals produced are shown in Table 6, because 95% of the residuals produced are coagulants of softening sludge. They will be stressed in this section. Major water treatment plant residuals, solid liquid residuals. First is alum sludge, second iron sludge, polymeric sludge, softening sludge, SFWB, if SFBW, spent GAC or discharge from carbon systems, slow sand filters, cleanings, residuals from iron and manganese removal plants, spent pre-coat filter media. Liquid phase residuals, ion exchange regenerant brine, regenerant from activated alumina, reverse osmosis reject. Gas phase residuals are air stripping of gases. The most logical sludge management program attempts to use the following approach in disposing of the sludge. First, minimization of sludge generation, chemical recovery of precipitates, sludge treatment to reduce volume, alternate disposal in an environmentally safe manner. Sludge production and characteristics. In water treatment plants, sludge is mostly commonly produced in the following treatment processes: pre-sedimentation, sedimentation, and filtration. Pre-sedimentation, when surface water are withdrawn from watercourses that contain a large quantity of suspended materials, pre-sedimentation prior to coagulation may be practiced. The purpose of this to reduce the accumulation of solids in subsequent units. The settled material generally consists of fine sands, silt, clays, and organic decomposition products. Softening sedimentation basin. The residues from softening by precipitation with lime and soda ash will vary from a nearly pure chemical to a highly valuable mixture. The softening process discussed earlier in this chapter produces a sludge containing primarily CaO3 and coagulation sedimentation basin. Aluminum or iron salts are generally used to accomplish coagulation. The chemistry of the two salts was discussed earlier in this chapter. The pH range of 6 to 8 is where most water treatment plants effect and coagulation process. Spent filter backwash water and mass balance analysis. Minimization of sludge generation for sustainability. The minimization sludge generally can have an advantageous effect of the requirement and economics of handling, treating, and disposing of water treatment plant sludges. Minimization also results in the conservation of raw materials, energy, and labor. There are three methods to minimize the quantity of metal hydroxide precipitates in the sludge. First, the changing of the water treatment process to direct filtration, substituting the other coagulants, and in particular using polymers that are more effective at lower dosage, conserving chemicals by determining optimum dosage at frequent intervals as raw water characteristics change. Sludge treatment. The treatment of solid liquid waste produced in water treatment processes involves the separation of the water from the solid constituents to the degree necessary for the selected disposal method. Therefore, the required degree of the treatment is a direct function of the ultimate disposal method. Sand drying beds. Sand drying beds are operated on the simple principle of spreading the sludge out and letting it dry. As much water as possible is removed by drainage or and the rest of the water must evaporate until the desired final solid concentration is reached. Sand drying beds have been built simply by cleaning an area of land, dumping the sludge, and hoping something happens. Freezing treatment. Dewatering sludge by either of the non-mechanical methods may be enhanced by physical conditioning of the sludge through alternate natural freezing and thawing cycles. The freezing thaw process dehydrates the sludge particles by freezing the water that is closely associated with the particles. The dewatering process takes place in two stages. The first stage reduces the sludge volume by selectively freezing the water molecules. Next, the solids are dehydrated when they become frozen. Centrifuging. A centrifuge uses centrifugal force to speed up the separation of the sludge particles from the liquid. In a typical unit, sludge is pumped into a horizontal cylindrical bowl rotating 800 to 2000 revolutions per minute. Polymers used for sludge conditioning also are injected into the centrifuge. The solids are spun to the outside of the bowl where they are scraped out by the screw conveyor. The liquid or centrate is returned to the treatment plant. Two types of centrifuges are currently used for the sludge dewatering: the solid bowl and the basket bowl. For the dewatering water treatment plant sludges, the solid bowl has proven to be more successful than the basket bowl. Vacuum filtration. A vacuum filter consists of a cylindrical drum covered with a filtering material or fabric, which rotates partially submerged in a vat of conditioned sludge. A vacuum is applied inside the to extract water, leaving the solids or filter cake on the filter medium. As the drum completes its rotational cycle, a blade scrapes the filter cake from the filter and the cycle begins again. Continuous bulk filter press, or CBFP. The bulk filter process operates on the principle that bending a sludge cake contained between two filter belts around a roll introduces shear and compressive forces in the cake, allowing water to work its way to the surface and out of the cake, thereby reducing the cake moisture content. Plate pressure filters. The basic component of the plate filter is a series of recessed vertical plates. Each plate is covered with cloth to support contain the sludge cake. The plates are mounted in a frame consisting of two head supports connected by two horizontal parallel bars. Ultimate disposal. After all the possible sludge treatment has been accomplished, residual sludge remains and must be sent to ultimate disposal or used in beneficial manner. Of the many theoretical alternatives for ultimate disposal, only three of the practical interest: co-disposal with sewage sludge, landfilling, beneficial use. And that was my report about water treatment.